So, welcome back. Today we're going to start getting serious, learn how to scale up reinforcement learning to real practical problems. By the end of today's class, hopefully you'll be able to go off into the world and actually program interesting reinforcement learning agents that can solve problems. In fact, we'll see state-of-the-art results, and you'll really get to the point where you're there, where you can see the whole algorithms do policy evaluation, do control, using function approximators to represent the value function. That's the key idea for today. The outline is going to be fairly simple today. We'll start off just understanding the basic space we're working in, and then we're going to split things up into two different approaches. First of all, we're going to start with incremental methods. Really, this approach is to say you take some function approximator like a neural network, and incrementally, every single step you see some new piece of data, it comes in, and immediately online, you take some step to update your value function online. And then we'll start looking at more data-efficient methods that kind of look at the whole history of everything you've seen so far, and start to look at the whole set of data and start to exactly fit your value function to everything you've seen so far. So roughly we're calling those batch methods. You can think of this also as online methods. The split is a little bit grey, as we'll see, and there's certain methods which work very well here that build on some of the ideas that we use here. So it's not quite as clear-cut, but I think it's a helpful distinction to understand the space of value function approximation methods. So why are we interested in value function approximation? What's wrong with the story so far? Well, we'd like to use reinforcement learning to solve large, real-world, interesting problems. So how large do problems get? Let's just get a sense of scale first of all. So if we think about some of the problems that people have solved, I've worked a lot in games, and in games you often see numbers like this, where the game of backgammon is considered a very small game for working in games. That's got just 10 to the 20 states. If you work in something like Go, there's 10 to the 170 states. But if you work with robots in continuous state space, there's an uncountably infinite number of states in this domain. So something's got to give. You can't just build a table anymore. The approach we've seen so far of just building a table and having a separate value for each state in your state space is just not practical. It's not going to work. It's not going to scale up to these interesting problems. So we need some method that scales up, and regardless of the size of the state space, we want to be able to get methods that work. We'd like methods that work with infinitely large state spaces, and you just happen to build a function approximator that estimates the value of just the parts of the space which you visit and know about, and which generalizes across parts of those space so that you don't separately represent the value of being here from the value of 1 millimeter over to the right. Intuitively, the value of those states should be pretty similar, and we want our value functions to understand that generalization without having to separately store a distinct value for each of these states. So that's the goal of today's lecture, is to understand how to achieve that generalization and to build up efficient methods for both representing and learning value functions in reinforcement learning. In the next class, we'll look at other approaches to using function approximation for policy space algorithms rather than value-based. We'll look at policy-based algorithms. But today we're really going to focus on value functions. How can we scale up? Value functions have been the central idea we've seen so far. And so in particular, we want to know how to do the core ideas that we've seen so far, both prediction, how to evaluate a policy, and also how to do control. These are the main subjects of the last two lectures, and we want to scale them both up. We want to be able to achieve good results with both of these ideas, both of these paradigms. So here's the basic idea in a nutshell. So far, we've really looked at this value function. We've had some value function v of s, and this v has represented some kind of lookup table. So for every state, or for every state action pair, there's been a single value stored. So for v, there's been like a single value per state, and we built this big table that said, for every distinct s, there's going to be a value v of s, and we were then able to build algorithms that manipulated those v of s's to figure out the problem and pick the right actions and solve the MDP. When we wanted to do control, if you remember, with control, we need to be able to pick our actions without using a model if we want to do model-free control. So we needed to use an action value function, q, that lets us consider for each state and for each action separately, what's the value of taking that action A in that state S. And this q, this action value function was sufficient to do control, because if we have this thing, we can immediately pick our actions by maximizing over our A's in each state, S. But again, so far we were just restricting ourselves to this giant table that has for every state and also for every action now. So think of this as like a two-dimensional table for all states in your state space and all actions in your action space. We had a separate entry in the table. Okay. And so let's be specific about the problem now. There are just too many states and or actions to store in memory. That's the first problem. But also, even if you can store it in memory, if you've got such a vast state space, like let's say you fill up your whole memory, you've got, a few gigabytes of memory, maybe you can build just a really, really large table and represent your MDP. But even if you do that, it's going to be too slow to learn about them all. In practice, we don't want to see trajectories that estimate the value of each of those states and actions separately. It's just going to be too slow. You need too much data. And so what's the solution? The solution is value function approximation. And we can basically represent the idea very simply in this following way. So what we're going to do is we're going to consider the true value function, v pi of s, as just some function mapping from s to the true value of v of pi. And what we're going to do is try and build some function that estimates this thing everywhere. So if you feed it in any s, it will give you some estimate of this v pi of s. And the way we do that, we're going to consider parametric function approximators that have some parameter vector w. So w is just some vector of weights. Think of this as the parameters of your neural network, or if you have a linear combination of features, it's going to be the weights of those features. And we're going to estimate our value function by building some function approximator that fits this thing across the whole state space. So we're going to try and fit this using some compact representation that's going to have a smaller number of weights, typically, than the number of states in the state space. So using a small number of parameters, we can now fit this thing everywhere, and we don't have to have a single entry for each state in the state space. And alternatively, we can do the same idea for the action value function, where we can try and fit the true action value function, q pi, which tells you how good is it to take action A from state S. And we're going to just consider that as this big function. That for any S and any A, we should be able to query this function. And we want to fit that function for all S's and all A's. We want to just fit this thing so that now if we feed in our S and our A, we're just going to have some vector of weights. Again, this could be the weights in your neural network. And we're going to try and fit some function approximator that estimates this thing everywhere across the whole state space and the whole action space. I'm just going to think of that as a big function and try and fit that function. And what this is going to enable us to do is not just reduce the memory. So we can reduce the memory if there's a smaller number of weights than we had states. It's not just going to reduce the memory, it's also going to allow us to generalize. And the reason it allows us to generalize is because we can fit our function to states that we've seen, and we can generalize to states that we haven't seen by querying our function approximator at points that we've never actually seen so far. And the way we're going to do this then, so we'll get into more detail so we don't have to understand everything from this slide, but the way we're going to do this is basically, we're going to think of this parameter vector, the weights of our neural network. We're going to update these things using the methods that we've seen in the last couple of lectures, Monte Carlo learning, TD lambda, and so forth. That's going to give us the targets for adjusting, for fitting our function approximator so that we can start to understand how to get the right value function. But before we do that, what we're going to do is, before we understand how to do the Monte Carlo or TD learning, we're just going to focus on what it means to do function approximation with a value function. So this slide basically shows us 3 different types of function approximation we can use with value functions. So these are like different architectures you could use. I tend to think of a neural network as a canonical black box function approximator, but you can use anything you like as this black box, any function approximator at all. They're all valid for reinforcement learning. Okay, and the idea is, if we're just trying to do state value function approximation, you've got this black box here, you feed in your state here, you've got something like a neural network that's going to kind of represent, this wiggly line is supposed to represent the fact that there's some internal function that this thing is trying to fit and represent, using some internal parameter vector w. And the way in which w affects this is just part of this black box. We don't worry about that. And what this thing is going to spit out is the value function at this query state s. So we feed in s. This thing estimates how good is it to be in s. So we feed in, I'm in this state over here, and this thing says, aha, you're going to get 7.6 units of reward discounted over the rest of your trajectory. Now, when we do action value function approximation, we've got 2 choices. We sometimes call this action in and action out action value function approximation. So in the action in case, what we're going to do is say, okay, I'm in this state here, and I'm considering this action here. How good would that be? And there's this black box here which is fitting some function across all states and all actions using some parameter vector w, and it spits out its estimate of how good it is to take that particular action in that particular state. Sometimes it's more efficient to use a different form. It's equivalent in its, the actual data that it's representing is the same, but it leads to a different training algorithm and sometimes a more efficient or less efficient result depending on the context. And now we're just going to say, hey, a state comes in, and we want our function approximator to tell us the value of all actions that I might take. So just the advantage of this is in a single forward pass, this thing can spit out the values of all the different actions. So we use this in Atari, for example. In one forward pass, we can say how good is it to move the joystick left, to move the joystick right, up, down, press the fire button. And just in one forward pass of your neural network, you get all of the information required to be able to make a decision. You don't have to feed it back in with different actions again and again and again. So these are all mechanisms for value function approximation. And the basic idea you should be trying to get your head around is that there's some representation of how good it is to be in a particular state, and we're trying to generalize across the whole state space using this sort of tunable parameter vector. So we're going to try and fit something to the true value function. So we want the shape of this internal kind of curve, this surface we're building, to be as close as possible to the true value function, so that now for any state that we query, we get the right answer. I'm going to train these things up to give us the right answer. And the way we do that is how the reinforcement learning comes in. Is that clear so far? Good. So let's open up the black box a little bit now and ask the question, well, what should it be? What type of function approximator? So hopefully, during your experience of the machine learning masters or whatever else you're doing, you've come across a whole variety of different function approximators for supervised learning or perhaps unsupervised learning. Some of the most common ones are listed here: linear combinations of features, neural networks, decision trees, nearest neighbor, Fourier or wavelet bases. There's a whole bunch of different things you might try. And you might ask, well, how can I navigate this sea of possible different function approximators? So for reinforcement learning, well, at least for this class, what we're going to do is focus on differentiable function approximators. So these are function approximators where it's relatively straightforward to adjust the parameter vector because we know the gradient of our function approximator. We know how, if we change these w's, these things tell us if we change the w's, how will that affect the v that comes out. So we know that gradient. If we know that gradient, there's a set of tools that we can bring to bear which allow us to do a certain class of algorithms that can be quite efficient, incremental, have nice properties. So for example, we're going to focus today on linear combinations of features as the canonical case. We'll see a little bit more what that means, but also allow for nonlinear function approximators like neural networks. And these are examples of differentiable function approximators where we know exactly how, if you change the W in your neural net, we know exactly how that affects the outcome, because you do a backward pass on your neural network, that gives you your gradient. Similarly with these linear combinations, we know exactly how the gradient of these things. So that's the representation. We want a representation that's differentiable, but what about training these things? Well, what's special about reinforcement learning compared to supervised learning is that in practice we end up with this non-stationary sequence of value functions that we're trying to estimate. If we're trying to estimate v of pi with this thing, we want this thing to evaluate our current policy, but our policy is changing. Our policy is going to improve. Like when we start to do control, we're going to start off with, say, some random policy. We want to evaluate that random policy, fit a value function to it, and then we're going to improve our policy, and we want to fit that new, better policy, and then we're going to change the shape of this is going to sort of slightly adjust as we get better and better at navigating our domain. Sometimes it dramatically changes. You figure out how to get into a new room that you've never seen before. The shape of your value function suddenly changes because you discovered a big treasure in that room or a pit of snakes or whatever it is. So we need to allow for non-stationarity in our in our function approximator, in the way we train them. And we need to allow for non-IID data. This is not supervised learning. The data that, as it arrives in trajectories that we're following, and where I am now is very highly correlated with where I am at the next step. And so IID training methods are typically not effective, or at least we need to be smart about how we make use of them. So that's the challenge. We're going to try and make use of these tools, put them together in a way that lets us do RL at scale. And the methods are relatively straightforward. Okay, so we're going to start by looking at incremental ways to do this using stochastic gradient descent to achieve incremental value function approximation. And then we're going to move on to batch methods such as least squares methods. Okay, so let's start off with gradient descent. So first of all, show of hands. So who is familiar with stochastic gradient descent? Good. Okay, I think that was almost everyone. I'll go through it briefly. I think it's good just to make the notation clear, make sure even if you're familiar that we're going to make heavy use of this over the next few slides. So we're going to consider some function. This is just gradient descent in general before we move to our value function approximation. So let's just consider some differentiable function j with parameter vector w. And we're going to use this definition of gradient, this sort of grad w notation. And what we're going to find the gradient vector to be is the gradient of partial derivatives with respect to each of our parameters in turn. So this vector basically tells us the direction of steepest descent, or steepest ascent. And we're going to follow this downhill. So this thing tells us, if I'm on some surface, which way is it to go down? And I want to follow that down my surface in the steepest possible way. And our algorithm is simply to say, to find a local minimum of this, we're just going to adjust our parameters in the downhill direction. So we're going to adjust our parameters to move down and down and down until we minimize this, this function, which we haven't defined, but this is our objective function. Or some objective that gives us a surface, we want to move down to find a minimum of that objective function. And all we're going to do is adjust our parameters a little bit downwards, that's the minus here. The half is just to make everything neat in the maths. Some step size in the direction of our gradient. So that's gradient descent. And so what we're going to do is plug this into value function approximation. So for this slide, let's imagine that someone tells us v pi. Let's imagine we're doing supervised learning for a minute. Let's imagine there's an oracle that says, here's the correct value for v pi. So what would it look like? What would our algorithm look like? So if we had this v pi oracle, then we could just minimize the mean squared error. It's like the oracle says, aha, you should have done this. Your value for this state should have been 7.3, but you actually got a value of 7, so that gives you an error term of 0.3. And in expectation, over all the states that you visit, there's some expected error, and what we want to do is to adjust our parameters in the direction that minimizes that expected error, the mean squared error. So we can do that using gradient descent. So we just, again, move a little bit in the downhill direction, adjust our parameters downhill. And now our j that we're going to plug in is this mean squared error. So our objective is to minimize the mean squared error between what we thought the value was going to be and what the oracle tells us the value should be. So we want to minimize that error by gradient descent. So all we're going to do is plug that in. So we've got this mean squared error here. So how do we minimize this thing? Well, we're going to apply the chain rule to this. So we've got this squared error here. So if we apply the chain rule to this, we end up with this error term multiplied by the gradient of this error term. But our oracle is just some constant. It doesn't depend on our parameters. So the gradient of this thing is just the gradient of our function approximator, b. So we get this term here. So to do gradient descent, all we need to do is move a little bit. So forget the expectation for a minute. That's just going to be averaging over all the samples we see. We're going to move a little bit in the direction of the error that we see in each state, multiplied by the gradient. And then the way to deal with the expectation is by using stochastic gradient descent. So instead of doing a full gradient, instead of explicitly computing this expectation, all we're going to do is we're going to sample a state. So we're going to randomly sample a state by just seeing which state we visited. We're going to look at what the oracle says in that state, v pi, we're going to look at our estimate. This is what we thought the value was going to be. We're going to look at the error term here. And we say, okay, we'd like to adjust our parameters so as to correct for that error term. So we've got a step size multiplied by the error, and now multiplied by the gradient. So the gradient essentially tells you how to adjust the parameters so as to move you in a particular direction. So you've got this error that you want to correct, and the gradient tells you how to correct it. And so in expectation, you can see that if you visit all states according to a distribution under your policy pi, then in expectation, we're going to arrive back at minimizing the mean squared error. And the beautiful thing about stochastic gradient descent is that even if you change things online, then you still arrive at minimizing this particular term if you control for step sizes and so forth appropriately. So literally every single step, incrementally online, all you do is you take a step, you look at where you've arrived, you make a prediction of what your value is going to be, the oracle tells you what the value should have been, you immediately adjust your weights, and you move on to the next step. And if you keep doing that repeatedly, then stochastic approximation theory tells us that this really will move you downhill and minimize the mean squared error between your function approximator and the oracle. You're fitting the oracle's predictions across your whole state space that you're visiting. And we don't need to know or worry about this expectation anymore. Okay, so is that clear so far, apart from the fact that we've cheated? So clearly this is cheating, right? We've used this oracle. So we're going to start to deal with that. Before we do that, let's try and get concrete about what this looks like in at least a couple of special cases. So this is probably the commonest case that you see. You know, if you sample a random paper from the reinforcement learning literature, you would see an awful lot of linear function approximation using features. So what do we mean by features? Well, let's define a feature vector. So a feature vector is basically each of these features is something which is just something which tells you something about your state space. It can be anything you like. It could be like a landmark. You know, how far is my robot from each of these landmarks could be my feature vector. This could say I'm 3 meters from the wall over there, and I'm 2 meters from the wall over there. And that could be my representation of where I am in the state space. And the feature vector throws away a lot of information. I'm no longer considering exactly what I'm seeing, and I'm compressing all of my knowledge into this feature vector. But if these features are good, it can make the learning problem much easier. It could be, you know, some trends in the stock market, or if we're playing a game, it could be, you know, which configurations of pieces or pawns are present on a chessboard. These are all valid choices of feature vector. And each feature is just one thing, one number telling you some piece of information about your state. And the collection of these features is trying to summarize in some compact way what's going on in the state. Okay, so let's assume for now that someone gives us a good feature vector. So we're not going to address the discovery problem of where these features come from. If you want to do that, you can use a nonlinear function approximator like a neural network, or all kinds of more sophisticated methods that we won't go into. And now, how do we use these features? Well, the simplest way to make use of the features is to make a linear combination of those features. So we're going to estimate the value function by basically combining them together with a weighted sum. So this basically says I'm now going to estimate the value function of being here by saying, okay, so I'm going to have some weight that tells me how good I think it is to be a certain distance from this wall, and how good I think it is to be a certain distance from this wall, and I'm just going to take a weighted sum of those things. So, you know, maybe I think I get one more unit of reward for each time I step away from this wall, and minus half a unit of reward each time I step away from this wall. And I would sum those together so that for any position I can work out exactly my estimate of how much future reward I'm going to get based just on those two features. And so, you know, clearly this is not going to be a perfect representation unless our features are extremely sophisticated, but it can give a very compact and easy to work with representation of the state space. Give us a very nice way to represent our value function. So basically what this looks like then is we say for each of our features, we're going to take a particular weight. This is the jth element of our feature vector. And we're going to take the jth element of our weight vector now, and we're just going to kind of sum these things together. Or equivalently, we take a dot product of our feature vector with our weight vector, and that estimates how much future reward we're going to get. So the nice thing, one of the nice things about this sort of linear value function approximation is that the objective function, this mean squared error that we were looking at, that we want to optimize, like our measure of fit between the true value function and our estimated value, is now going to be convex. It's going to be a quadratic. You can see it's a quadratic because if we consider our parameters w, we've got this squared error here. And so if we consider our mean squared error, if we just ignore all the other terms, you can see that this thing is quadratic in w. Okay? So that means there's some bowl or other quadratic shape, turns out to be a bowl, representing basically our mean squared error, the objective function. And that's a very easy shape to optimize using standard optimization methods. In particular, if we follow gradient descent and we just move down this mean squared error, if we always take a downhill step, we will get to the bottom of our bowl. We will find the optimum mean squared error. So the nice thing about using linear combinations of features is that when we optimize them, you never get stuck in some local optimum. You always get the best correct answer if you follow your gradient descent for long enough. And the update rule is particularly simple. So we find the global optimum using this very simple update rule. And the reason it's so simple is because the gradient of this thing here is just the feature vector. The gradient of this with respect to our weights is just the features. We're just everything is linear in our weights, so we just need to multiply by our features. And so the update rule becomes very simple, which is to say the change to w, the change to our weights of our linear combination. Again, if we're given an oracle here, we're going to look at what the oracle said the value of this state would be. So I'm over here, I look at my features, I see how much I estimate. I'm going to come up with some estimate and say, okay, I think I'm going to get 6 units of reward. I'm going to see my error with what the oracle said. And now I'm going to move a little bit, step size, in the direction of how to correct this error. And what we're going to do is we're going to basically look at each of the features and say, whichever one of these features is on or highest is going to take the most credit for that error which I see. So we basically move things in the direction whether to adjust things by basically changing the weights which have the most active features. So if a feature is off, like imagine you're playing chess and you've got a feature to say, have I got a queen? And now you see some error in a position where you don't have a queen, and you actually end up thinking now you're going to lose the game before you thought you were going to win the game. You wouldn't update that feature because you were in a position where you didn't even have a queen at all. So you only adjust things where the features are essentially on and active. You don't make any change to situations where your features are off or inactive. Okay, so linear combination of features, very simple, very straightforward. And it basically boils down to this very simple update. You move your weights a little bit in the direction of the error multiplied by your feature vector. And the feature vector tells you how to adjust things so as to correct in the direction of where things were really on. Like if I'm really far away from this wall and I'm estimating that the further away I am from this wall, the more reward I'm going to get, then that wall, that feature from that wall is going to be, giant. That's going to be the thing which should dominate this term here. So I really adjust that weight more. Okay. Clear? I want to connect what we've just talked about with the previous classes. So I really don't want you to have the feeling that, oh, now we're talking about value function approximation, and in the last class we were talking about table lookup, and these are two totally different classes of algorithm. They're the same. Right? Table lookup is a special case of linear function approximation, and we can see that by basically defining some special features. And we can basically build up this special feature vector that says, am I in state 1? If I'm in state 1, have a feature value of 1. If I'm not in state 1, have a feature value of 0. We can do the same thing for state 2, same thing all the way down to the final state. So now we're going to have this enormous feature vector with one feature for each state we're in, and all of them are going to be 0, except for the state which we're in right now. Which is going to say, aha, I'm actually in state S734, and that one would have a 1, and everything else would have a 0. If we use that representation, if we use this X table as our feature vector, then when we take our dot product between our feature vector and our weights, we see that we're just picking out one of those weights. So we've basically got a weight for every single entry of our table. We've got a weight for every single state in our state space. And depending on which state we're in, we're just picking out one entry from our table. So this thing just lets us select the right entry from our table. And now we're back to having a table lookup representation. This is our table. Okay, we've got one entry for each state. We pick out the entry of that state according to the feature, the state we're actually in at any given time step. Okay, takeaway from this slide, table lookup representations are a special case of value function approximation. We don't need special machinery to deal with them. Everything we've seen so far is a special case of what we'll talk about today. It's just a particularly convenient mechanism to use or to think about. Okay, so we've cheated. We've really cheated. We've imagined the existence of this oracle. That's totally out of the spirit of RL. I mean, this just doesn't happen in practice. The whole point of reinforcement learning is there's no supervisor to tell us, hey, the right answer was 7.3. We need to figure that out directly from experience. So how do we do that? What's the method we use? Well, we're going to use the same fundamental methods that we've seen in the last two lectures. We're going to use Monte Carlo and temporal difference learning methods to give us a target to use for our function approximator instead of the oracle. So far we basically assumed that we were given this v pi of s. But we know that we've seen in the previous lectures that we can get some targets that estimate v pi of s directly from experience. How do we do that? Well, if we use Monte Carlo learning, then this target will just be the return. So we use the return as an unbiased estimator of v pi. And so the idea is that if we substitute in, now we're just going to do this by substitution. So think of this as like copy and paste exercise, in that we've developed an algorithm for supervised learning. And now what we're going to do is wherever we saw v pi before, we're going to copy and paste some other target instead that we arrive at through a reinforcement learning method. So the first thing which we're going to paste in is the return. So we're going to basically take the return here, and what this algorithm says is, the change to our feature vector, or to our weights, the change to our weights is we're going to move a little bit in the direction of the error between the actual return. So, I'm now going to say, I'm going to start here, I'm going to estimate using my function approximator, I'm going to come up with some estimate that says I'm going to get 10 units of reward, and then I'm going to see what happens, run my entire trajectory out, discover that I actually get 12 units of reward, generate an error of 2 units of reward, and update my weights a little bit in the direction of that error multiplied by the gradient of my function approximator that tells me how to move in the direction that changes that, to change my values. So that's how to plug in Monte Carlo. We basically take our supervised targets, our v pi's, and we replace them with the return. So now we're just updating things. We're fitting our value function towards the returns. The returns become the supervisor. So we're kind of doing supervised learning on the returns. Is that clear? If we use TD learning, we're going to use a different target as our estimate of v pi. We can use our bootstrap estimate. We can use the TD target. So now we're basically going to say, instead of waiting all the way until the end of the episode and getting some estimate of the return, I'm going to use the TD target. I'm going to start in some state. I'm going to estimate that I'm going to get 10 units of reward on this trajectory. Then I'm going to take a step, see that I get, say, 1 unit of reward, and then estimate that I'm going to get 8 more units of reward. And so I'm going to say, okay, well, my TD target will be the 1 plus 8. So I think I'm going to get 9 more units of reward. And now we're just going to do, just like supervised learning again, we're going to treat that as our target. We're going to adjust our function approximator so as to fit these values that we're predicting. So now we're going to use that as a training sample. We're going to try and fit our function approximator towards that example where we think we're going to get 9 units of reward. So we do that again by moving a little bit in the direction of the error between our 9 units of reward and our 10 that we predicted before, multiplied by the gradient that helps us achieve that, to realize that change. We can do the same thing with TD lambda. I won't go into the details of TD lambda today. You can look at the previous lectures. same idea. We use the lambda return. So this is the thing which sort of interpolates between TD0 and Monte Carlo learning. Whatever our lambda return is, we treat that as the target, and we fit those lambda returns that we see. We use those as the targets for our function approximator. So what's this look like? So we can think of this as a process that looks a lot like supervised learning. So when we do Monte Carlo learning, we're basically going to use the return, and we're going to build some training data. Think of this as building training data, but we're doing this kind of incrementally. Like we first of all see state S1, and we run a trajectory from it, and we see that we got a return of G1. And then we visited state S2, and from S2 we got a return of G2, all the way up to our final state, our trajectory or our, wherever the agent got to, and its final return here. So that's the data that the agent's seeing. It's seeing this data, it's seeing all of these states, and from each of those states we've got some estimate of the return, which we're using from our Monte Carlo learning. Okay, so our Monte Carlo, we're just rolling out and seeing how much reward we actually got from each of those states. Think of that as like your training data. And so now, what we're going to do is basically, just like supervised learning, we're going to treat this as a data set, and we're basically going to adjust our function approximator so as to fit the G's and estimate what the G's will be from any one of these S's. So this is just like supervised learning. And the simplest case is using linear Monte Carlo policy evaluation. So this is the same as the last slide, but now all we're going to do is substitute in our linear function approximation, so the gradient just becomes the feature vector, and all we do is we plug in the return, so we adjust the weights of our linear combination a little bit in the direction that corrects our estimated value towards the return. And we know that this has to work because we're just doing stochastic gradient descent. Stochastic gradient descent converges to an optimum, and we know that Monte Carlo learning gives us an unbiased estimator of the true target. So essentially it's as close as you can get to an oracle. It's just a noisy oracle. And so this will work, it just may be a little bit slow. So even if we use nonlinear value function approximation, Monte Carlo will converge to some local optimum, or in the linear case, it will find the global optimum. We can do the same idea with TD learning, but now we've got this bias sample. So we don't have the true oracle anymore, we don't even have a noisy oracle, we just have some biased estimator of the target. So what I think will happen after one step, and then invoking my own function approximator again, so I get the reward RT plus 1, and then I have to query my own function approximator to estimate how much reward I'm going to get for the rest of the trajectory. That's how we get the TD target. So this thing is biased because we're having to go through our own neural network or our own linear function approximation to figure out what these values will be. And so this gives us a biased sample of the true value. But we can still, once we've accepted that we've introduced a bit of bias, we can do the same idea. We can create this data set. What's the data set look like now? Well, it's like for each state, we have a TD target. So it's like I was in this state, and I saw one step of reward, and then a value function estimating how much reward I was going to get from that point onwards. Then I was in another state, and I got one step of reward plus the value function after that. And I can build up a whole data set that basically uses these TD targets as like training data. We start to fit our value function towards these TD targets. So let's do the simplest case again. Let's consider linear function approximation. So now what we're going to do is plug in our TD target. So we're going to basically say we're going to adjust our weights a little bit in the direction of the error between what I thought the value was going to be and my one-step estimate of the value, the TD target, like after one step, how much do I think I'm going to get? Treat that as the target. We're going to see that there's some error. Like if you're playing a game, this could be the thing that says, before I played the move, I thought I was winning, and then I played my move. It's like, oh no, I actually just saw that I blundered, and I'm going to, lose my queen. And so that generates an error between what you thought was going to happen and what actually happened. We use that error signal to correct where you started. Now you think, oh, I was actually losing all along. I just hadn't realized it until I took that step. And now this gradient tells you how to adjust your function approximator to make it more like you thought you were losing in the first place. And so we can compactly write that in the following way. We update our parameter vector, step size multiplied by TD error multiplied by feature vector, or the gradient in the more general case. Feature vector in the linear case, gradient in the nonlinear case. Good question. I've been quite suspicious that you're all so quiet. It's like you're normally like asking questions every 5 seconds. Good.
So you're saying that you generate this data set and then you're doing that supervised learning on the data you've generated. So you do this after every step, or is it after the end of each?
Yeah, great question. So I'm just actually trying to give a flavor of how this relates to supervised learning, so you can think of what it means to train this function approximator. In practice, we're doing everything incrementally. This is the first half of today's class. Incremental, online, updates. So every single step, we're going to take a step, we're going to see, we're going to generate our TD target. So like I'm in this state, I thought I was going to get some value, I take my step, I get some new estimate of the value, I generate a TD error, I update my weights immediately, and then I move on to the next step. So the data set idea we'll come back to later when we do batch methods, but it's just to see that there's a relationship between this and supervised learning, that we're doing something where we're associating for each state, we're associating each state to some target, and we're just playing with what that target is. We're playing with whether that target's an oracle, whether it's the Monte Carlo target, whether it's the TD target, or whether it's like a TD lambda, a lambda return. Okay, and even though this is biased, it's really important to note that there's a famous result by Tsitsiklis and Van Roy that shows that linear temporal difference learning still converges if you use linear function approximation. Despite the fact that we've introduced this bias, it still converges close to the global optimum, where close depends on things like your discount factor. And then finally, I won't dwell on this, we can do the same idea with TD lambda. And now the data set, if you like, the data that we're generating, again, we're still doing this online, but the association that we're making is each state we're associating with some lambda return now. So the lambda return is this mixture of all your n-step returns. And so we're going to try and basically learn to make our value function fit it to these lambda returns. We want to take some weighted combination, lambda weighted combination of what I think is going to happen after 1 step, after 2 steps, all the way up to infinite steps, and make our weighted combination of all of those estimates, call that our lambda return, and then fit our value function at each of these states towards those targets. And we're going to do this incrementally, step by step, but conceptually there is this data set that we're kind of moving through. And so we can do that either using the forward view. So the forward view has this flavor where we move a little bit in the direction of the lambda return, the error between the lambda return and what we thought the value was going to be, multiplied by the gradient in the nonlinear case, or the feature vector in the linear case. And there's an equivalence, again, just as we saw in previous classes, there's an equivalence to this backward view where you can use eligibility traces and you can make something which is now truly, we want to achieve online updates, where you take a step, you update. And you can do that using eligibility traces. So briefly, what do the eligibility traces look like? I think someone asked in a previous class, what's the size of these eligibility traces? And when you use function approximation, the eligibility traces are eligibilities now like on the features or on the weights of your parameter vector. They're the size of your parameters of your function approximator. They're not the size of the state space. So the eligibility basically says, look, each time you take a step, we're going to decay our eligibility a little bit, but then increase it in the direction of all the features that you've seen. So this is kind of remembering all the features that you've seen so far according to their magnitude. So the eligibility trace is kind of accumulating credit for the things that happen most and the things that happen recently, and then it decays over time again. So kind of each step we add on, hey, this feature was on, I had a queen at this step, and I had 7 pawns, so those are the things which contribute at this step. Maybe at the next step I only have 7 pawns, those would be the features that contribute there. And you kind of take the sum of all the things which are on and active, or the large features, and they kind of get, the more something occurs in your eligibility, the higher your eligibility is pushed, and that feature will then get updated the most when you actually see an error. And then the TD error is generated in the usual way, and we update our weights now a little bit in the direction of the TD error multiplied by this eligibility vector. So we update our weights proportional to the TD error and how much each of those weights is to blame for the error that we've seen. And without going into the details, again, there's an equivalence where if you do this at the end of the episode, if you were to just gather up all your changes until the end of the episode, you would find that you make the same updates forward and backward. These things are equivalent. Right. So just before we do control, is everyone good so far? This is like the main point of this class is these last few slides. And if you're lost, you should ask now, because it's just going to get, we're going to build on it and do more things. Yeah.
So G lambda and like the target in these slides depends on the value function.
Yes.
So why don't we have a term for that dependence in the update?
Okay, great question. So the question was, why does the gradient only depend on our predicted value function? Let's go back to the simplest case with TD0, and because we can still ask that question already here. So the question is, when we take the gradient, why don't we take the gradient of both the target and our function approximation? Why is the gradient only of our function approximator? The answer is, it's a slightly tricky answer, okay? One way to answer this is to say, we're doing TD. TD means that you kind of, you're always pushing things towards what happens later because you trust the thing which happens later. You don't want to reverse the flow of time. You don't want to update the estimate of where you end up later towards what happened before. Like if you have the gradient of both of these things, it's like you've kind of got a spring and you're pulling your value function of what happened afterwards towards the value function of what happened before. You're pulling them all together to try and reduce the error. And you can show, there's a very simple example where you can show, even in a table lookup situation with a stochastic MDP, if you do that, you will get the wrong answer. You will not find the correct value function. And the reason is that this trying to minimize for this error in this way doesn't, you need the flow of information to be grounded. You need to ground things, and the way you ground things is to go later in time. Like as you go later and later in time, you see more and more real rewards. And the more real rewards you see, the more you can trust what you've seen in terms of what's actually happened. You don't want to reverse the flow of time and update something where you saw a real reward towards something where you hadn't seen that reward yet. You will kind of get the wrong answer if you do that. And so putting the gradient on both terms is doing a little bit of that time reversal. It's doing both the forward and the backward direction. And there are variants of that which are not quite so bad as the way I've made it seem. The family of methods is called residual gradient methods. And so it's a well-known idea. People do this in practice, but it's also well known that if you just naively plug in the gradient here of this term as well, so if you just had the gradient of the error between these guys, you would get the wrong answer. You have to be a bit clever about taking expectations, and then that algorithm isn't actually practical, and you can't do it in incremental settings because you need two samples. And this version works well in practice, and you just need to be careful. It's intuitively, it's appealing when you first think about it to do what you suggest, but I would recommend against doing that unless you really know what you're doing. But there are cases where it's a reasonable thing. Okay. I'll come back to a related question in a minute, but thank you, that was a great question. Okay, let's move on to control. So we're going to use the same idea for control that we saw in the last lecture, where we're going to still build on our idea of generalized policy iteration, but now we're going to use approximate policy evaluation. So what we're going to do is we're going to start off with some parameter vector now, and we're going to say, okay, that parameter vector, that's going to define some value function. And what we're going to do is basically act greedily with a little bit of epsilon exploration, for example, with respect to that value function that we've defined. So this might be our neural network. We act greedily with respect to our neural network. That gives us a new policy. And now we want to evaluate that new policy, so we run some more data, we update the parameters of our neural network. That gives us a new value function. And now that new value function, we can act greedily with respect to that, and so forth. And again, just like in the last lecture, we're not going to go all the way to the top here. We're not going to waste millions of samples of experience trying to exactly fit our function approximator. Indeed, we know that if we're using a function approximator, we're not going to precisely be able to achieve equality here ever anyway. So what we're going to do instead is take some steps towards it, and then immediately update our policy. And in the most incremental case, where we just do TD for one step, we're going to do this every single step. Every single step, we're going to start evaluating our policy. We're going to update our neural network once, slightly adjust the shape of our curve, and immediately act with respect to that latest neural network to pick our actions. So there's no reason to wait until you've really adjusted your neural network an awful lot before you start picking actions again. You know, why not always use the freshest, most interesting information you've seen? And so that's the idea of this approach here. And we'll see some variants later, but you can do policy evaluation, where you do approximate policy evaluation. So again, we're trying to estimate the action value function now. So let's just back up. Like last class, we saw that there were two ideas. In order to do control, we needed to take generalized policy iteration, and add two new ingredients, where we needed to use the action value function Q, so that we could be model free and still be able to pick the greedy action. And we needed to have some kind of exploration, for example, using epsilon greedy. Those were the two ingredients that we introduced last week. And so we're going to use those same two ingredients, but now we're going to use our function approximator to get an approximate Q value. So think of this now like a neural network representing Q. We're just going to figure out the parameters of that neural network as best we can, then act greedily with respect to it, throw in some noise to get some exploration, continue our algorithm. So what happens? Does this really find the right answer? Does this get to Q star? Well, of course not, because it might not even be possible to represent Q star anymore. We've used some approximation, so we should expect, in the best possible case, is that we will have some controlled algorithm which gets closer and closer and closer to Q star. But it turns out even that is too much to hope for in the control case. We typically end up with algorithms which sort of oscillate around, and sometimes they get a little bit further before they come back in again. And there's some ball within which they oscillate, and they can kind of come in and out. But in practice, they tend to get very close to the right answer, and so all is well, roughly. So, the first ingredient is we need to do all the same things using Q instead of V. Okay, we need to think of how do we do this with an action value function. So let's just back up. We'll do the same steps again using Q, just to make sure it's all embedded nicely. So we're going to approximate the action value function. So now for any state and any action, we're going to build a function that predicts, with these parameters W, that predicts how much reward we expect to get from that state and action onwards. And then we're going to minimize the mean squared error now between our Q values and the true Q values for our policy. And so we build up our mean squared error. This is the expectation under our policy. So that, with respect to the states that we'll see if we just follow our policy and the actions that we see, we're going to look at the squared error and expectation, and we do stochastic gradient descent again. So just the chain rule, we have our error multiplied by the gradient. And so now what we're doing is we're moving a little bit in the direction of the error between the Q value that I estimated before and the Q value that my oracle gives me, if we have an oracle, multiplied by the gradient. And now, what does our function approximator look like? Well, let's consider the simplest case again. Using linear function approximation, we can now build features of both the state and action. So this might be, we might have one feature saying, how far am I away from this wall if I'm moving forwards? That might be one feature. And I might have another feature that says, how far am I away from this wall if I'm moving backwards? These are like functions of both the state and action which I take. And there's just going to be some number telling us each of these cases. And maybe it's just 0 if I'm not doing the action which I was interested in. Or maybe we generalize across actions. And so that's going to give us features, a feature vector, that tells us about the whole state action space. And so we can build up a picture of what this whole combined state and action space looks like, or what's the value of all of these things. And the way we do that, the simplest way, is by building a linear combination of features. We could also do something more sophisticated like a neural network. and then just follow the gradient. So the gradient update now collapses to change the weights, the direction, the step size multiplied by the error, multiplied by just the features, whichever features are on. So this was basically, in the example I gave, if I actually go forwards, then we would only update the feature corresponding to my forward action, because the other one would have a 0 value. Okay, we can plug in the same idea. So this is just the same machinery again. I'm not going to dwell on it for too long, where we can basically do exactly the same things with Q. We can use Monte Carlo learning. So now, if there's no oracle, what do we do? Well, again, we can use the return as a noisy, unbiased estimate of the oracle. We can use the one-step TD target, or we can use the lambda return, or we can do the backward view TD lambda to use eligibility traces. So all of these are just as before, but now we're using Q rather than V. And the reason to use Q rather than V is so we can do control. Once we have Q, we can just pick the max over our actions. We don't need a model. We can figure out what the next action we should take is, and continue to do our policy improvement steps. Okay, let's do an example. There's been a lot of slides without getting concrete. So this is probably the most widely used example in all of reinforcement learning. So if you were to pick up like a random paper on reinforcement learning, there's a very good chance it would have this mounting car problem in it. I'm kind of sick of seeing it now, so but you know, it's still, I think it's a good problem and it's interesting to think about. The idea is you've got this car here, it's stuck in this dip, and you can see it's kind of steep here, so how are you going to get out of this dip? The assumption is that your car isn't powerful enough to just drive straight to its goal here. So what it has to do is has to kind of just let go and roll backwards, drive forwards, roll backwards, drive forwards again, and build up enough momentum to actually be able to reach the goal there. And then the question is, well, how do you figure out that control strategy? How do you just do this, not saying anything about the MDP, about the dynamics, you know, do this all model free, we want to solve this. And now we want to do this using function approximation. So what's the state space in this problem? Well, the state space is the position of this car in this continuous state space, and it's also got some velocity, and so you can think of this as a two-dimensional state space, position in one axis and velocity in the other axis. And so the value function looks something like this, where you've got some surface saying for each situation this car might be in, like if it's here and going downhill at some particular velocity, you might find yourself, you know, at some point on this diagram and you want to know, well, how good is that? How much reward will you get? And of course, like usual, how much reward you'll get depends on the policy you're following. So to begin with, if you're just acting randomly, then the value function looks something like this. And so over time, what we see is that as the policy starts to improve, we start to see more and more shape emerging out of this function approximator. This is doing our generalized policy improvement using the SARSA algorithm. Okay, so SARSA, if you remember, it's literally the extreme case of this diagram here. It's the extreme case of this diagram where every single step we update our value function, in this case using a linear function approximator to estimate Q. Every single step we update Q, and every single step we act greedily with respect to Q to pick our next action, but we also flip a coin to see if we do something random to make sure we explore. That's SARSA. That's all it does. And the way that we update Q is using the one-step TD returns. So these guys here. So what's happening is we're on our mounting car, where, you know, in some situation, we have some prediction of what Q is going to be for the action. So we take some action, like trying to apply some acceleration. We've got some prediction of how much value we're going to get. Then we see that we actually end up falling backwards, back down the hill a bit. We see how much Q we now predict in our new state and the new action we will take from there. We adjust our function approximator towards that new Q value, So we think that where I was before and applying an acceleration, that the value should be adjusted, the value of this curve should be adjusted a little bit in the direction of those q values. And what that does is it's effectively pulling up or down this function approximator in the direction of what we now think the value should be. So every single step you see, you're kind of pulling up or pushing down this function approximator, the shape of this curve, the shape of this surface. And if you took a step and ended up in some situation where you think you're actually doing much better now, you suddenly reach the goal, that will pull up the whole shape of this function approximator. And this particular function approximator that's used for this example is what's called a coarse code, which is like basically lots of overlapping tiles of different shapes and sizes. And they all overlap, and anything which is actually active, which is on, will be pushed up when a particular state is visited. So you visit a state, you think, aha, the features which are on are all the ones nearby this. They all get pulled up, none of the other ones get affected, and you get generalization around the region of the tiles which are sort of active at that point in time. Okay, so that very simple function approximator is sufficient to express quite a complicated shape in the value function. And you see that there's these curves and complicated surface starts to emerge here, and you get these spiral patterns appearing until eventually you end up with something which looks like this. So this is actually using a different type of function approximator, a radial basis function approximator. You end up with this kind of spiral pattern in the position of velocity space. It's a really old figure, you can tell it's got handwriting on it. Wow. And you get this shape appearing, and this is an approximation of the optimal value function for mountain car. And so nothing is exact, like we're generalizing. We don't precisely know what happens for some point in between these things. This is a smooth function approximator that's interpolating within its tiles and estimating some of these values. But you can see that it works very well at getting this space, and this also scales up to much more complicated problems as well. Okay, does that give a bit more of a flavor of what's going on? Good question.
So in this example, you have a continuous state space with a continuous action space.
In this example, good question, sorry. In this example, there is a continuous state space, which is the position of velocity. The action space, you can do it in different ways, but in this particular example, the action space is either is discrete, so you basically get discrete choices of acceleration. So you either can not accelerate or accelerate, and the amount the accelerate is given. And for some class of interesting problems like this, often there's a class of problems called bang-bang control problems, where actually it's not interesting to consider the space between maximum acceleration and minimum acceleration, because you would always choose to maximize to one of those extremes. And so, yeah, but you can also do this problem with continuous control. But that's a different, that would require, so SASA would still work. The only question there is how you compute the max. If you've got continuous action space, computing the max is tricky, because you've got to do an optimization just to even find the max. Yeah, question?
In that example, couldn't we use a different representation of the state space and get a function with a much simpler shape?
So the question is, couldn't we use a different representation of state space to get a simpler shaped value function? So that's a great question. So I think the right way to think of this is to say that the state is what's given as part of the description of the MDP, and this is the true shape of the value function. Now, to learn this effectively, you can put in any features you want. So if you think that there's some features, like the features that you provide can indeed transform the shape of the value function to something much simpler. That's one of the reasons to use features. So if you know good features, you can transform this complicated spiral into something flat or something simple to learn. And that's putting knowledge in to simplify the shape of the problem. But this is the value function. This is v pi. V pi looks something like this, and we're just trying to approximate v pi. And so yes, indeed, you can put knowledge in to help figure out this shape of v pi more effectively. Okay. So we talked a little bit about using lambda there. So I just want to throw up this slide, which is like an empirical slide. It's an old one, but I think the lesson has been borne out time and time again since then. So I think it's still useful to see. So forget the accumulating and replacing traces. That's just two slightly different variants on how you use eligibility traces. the story is roughly that across a bunch of different environments, when you use function approximation and something like SARSA, the question is, should you use eligibility traces? And you almost always see some kind of picture like this. This is a cart pole example, this is mountain car. And you almost always have this picture where if you go all the way up to lambda equals 1 and use Monte Carlo returns, performance is really bad. It takes an awful lot of samples to actually get the right result. The variance is too high and you're killed by variance. If you go all the way to TD0, you do better than Monte Carlo. Bootstrapping gains you a lot of efficiency, but there's normally some kind of sweet spot in between, and the shape of that sweet spot depends on the problem and all kinds of things, but typically, having some bootstrapping helps, and lambda can find you something better than TD0. But the main point of this slide is to say bootstrapping typically helps, and so it's worth finding algorithms that are effective when we bootstrap. And so the natural question is, well, is it sound to bootstrap? Like, we know that following Monte Carlo is just like this noisy oracle. We're doing something just like supervised learning, and it must converge. But is that true for TD methods? Do they always converge? And let me put up one situation where they don't. So I'm just going to flash this at you without explaining the example. If you were to do something like this simple MDP, and you were to update instead of using SARSA and actually running on policy, if you were to update this by doing sweeps over the whole state space and doing your updates on all states, you end up with weights blowing up, basically. This is the number of iterations you get, and the weights can blow up. So TD isn't guaranteed to be a stable algorithm. There are situations where you can apply TD where it can blow up, and so it's important to know when it's safe to use TD and when it's not. So this is like a one-slide summary that roughly tells us when it's okay to use TD, when we're guaranteed for TD to converge to something, and when there's a possibility that it might diverge. So the crosses mean there's a possibility of divergence. Ticks mean guaranteed convergence to something close to the right answer. And so now we can consider if we're running on policy. So on policy, remember, means we're actually learning from the behavior we're running. So we run our trajectory, and while we're running that trajectory, we're learning about that policy that we're following. So Monte Carlo, great. Okay, it converges for table lookup, for linear, for non-linear. This is all for just policy evaluation so far. We're not talking about control on this slide. But for TD algorithms, if you run on policy and use non-linear function approximation, no guarantees, it can blow up. Like, the bootstrapping process can cause divergence, in theory. In practice, it tends to work okay, lots of success stories, but you can certainly construct counterexamples where it blows up. Off policy, even using linear function approximation, it's possible to construct counterexamples like the one we just saw, where TD blows up. So off-policy learning can be a little bit problematic, and I just want to mention some more recent methods. So methods such as gradient TD, also in the last few months there's another method called emphatic TD. These are methods which fix the issues that the TD algorithm has when it bootstraps, and we can see that, for example, gradient TD, this is a true gradient descent approach. So instead of just doing this gradient descent and then substitute in the TD target and hope that it's still a gradient, this is something which really follows the gradient of the projected Bellman error. That's a particular objective function, follows a true gradient. I don't want to get into the details now, but you can look it up. And so it is possible, just with a small correction term, that you basically end up with the same update with one more correction term, and it fixes the problems that we see with TD learning. So you can get convergence, but you have to just be a little more careful with TD. What about when we do control? Control is surprisingly problematic. Like, this whole framework of generalized policy iteration, it's very appealing. It gets very efficient algorithms. You've got these very aggressive steps where you take the greedy policy improvement step and you really try and make your policy as good as it can be at every time step. But essentially, we very rarely have guarantees. In fact, almost always we get chattering, which basically means that each time you improve your policy, you might actually make there's no guarantee once you use function approximation that your improvement step is really improving the policy. You might take an epsilon greedy step, but we don't have this guarantee anymore that that's actually making progress at every step, and you can kind of make progress, and then take a step away, and make progress, take a step away, and end up chattering around the optimal policy or the optimal value instead of ever converging to it. So cross here means catastrophic divergence is possible. This means that you chatter, like you're always getting closer but occasionally stepping away, but you never just kind of shoot off to infinity. Right. Okay. Questions before we start running out of time? Good. Yeah. The back there. Yeah, you.
I just want to know, when you say convergences, the weights that you mean that they're going to be fixed at a certain value?
So what does convergence mean? Convergence means that the parameters of your function approximator converge to some fixed point, and a secondary issue is that fixed point, the right fixed point that we want. And so what this really means is that we converge to a parameter vector that's close to the best parameter vector in the space for our function approximator. Okay. Yeah.
You said you can get catastrophic divergence in theory. Are there any of those x's where you would often get catastrophic divergence in practice as a common observation?
So yes, we'll talk about that in just a minute. So one of the so using neural networks, if you just naively throw in, say, Q-learning or SASA or something like this and hope that it will work, it very often blows up with a neural network, and that's because if you use some nonlinear function approximator with like these steep sides, you can really dramatically alter your policy, and your gradient can be very large. You can be kind of shoot off to some new situation. You can end up with these quite complex cycles where you think you're making progress, but now you change your policy and the value function changes in some way that changes the shape of this thing, and you can end up spiraling outwards. It's possible, and yes, it happens. With linear function approximation, I would say, in practice, even if you're running off policy, where we technically have a cross there, mostly it's okay. You sort of have to work a bit harder to break the algorithm. And I would say in practice, you don't necessarily observe divergence. And I'm going to talk about how to address the neural network issues in the next part. Okay, good. So I think we'll have time for talking about some of the batch methods, but I'll leave some to as a reading exercise afterwards. Okay, so let's begin with the motivation. So far we've talked about these gradient descent methods. They're very simple. The updates are really simple. You just move a little bit in the downhill direction, look at your error, move a little bit that way. But they're not sample efficient. We see our experience once, we take an update, we adjust our function approximator in the direction of that experience, and then we throw that experience away and we move on to the next one. That's not data efficient. We haven't made the maximum use of that data to find the best possible fit to our value function and hence the best possible policy. So the idea of batch methods is to try and find, in some sense, the best fitting value function to all of the data that we've seen in our batch. And the batch, in this case, is the agent's experience. That's its training data. It's its life. Like life is one big training set for an agent. And we're trying to basically now fit everything the agent's seen, find the best value function that kind of explains all of the rewards that it's experienced so far. So what does it mean to find the best fit? Well, one definition would be something like a least squares fit. So now, if we want to fit our function approximator to the true value function for our policy, we can, again, define some data set. This is just what we did before. We can say we've got some training set, which is our state and our targets. Like, let's say there's an oracle again. So let's say in state S1, the oracle tells us the value should have been this thing. So this thing is just whatever our target is. We're going to call it V1 pi. That's the oracle consulted for state S1. We consult the oracle for state S2. It gives us another value. That gives us our training set for all of the data that we've experienced. And we remember that whole data set. And now the question is, what's the best fitting value function for this whole data set? Well, we could do something like least squares, which would find the parameter vector that minimizes the sum squared error between the value function and the oracle across our whole data set. So if we consider this whole data set and look at the squared error between what we thought would happen here in the oracle, the squared error between what we thought would happen here in the oracle, and we want to just minimize the sum of all those squared errors across the whole data set. So that's what the least square solution does. So it's the sum over all time steps between the oracle value and what we thought would happen, all of those squared errors summed. And we can write that as an expectation over our empirical data set. So this ED means like an empirical distribution expectation over this sum, basically over everything we've seen so far. So we're trying to minimize some kind of mean squared error, the sum squared error, over all the data we've seen so far. So that's the least square solution. And it turns out there's a really easy way to find the least square solution. And it uses all the methods we've seen so far. And it's just called experience replay. And all it means is that now we make this data set a literal thing. We actually store this data set. So instead of throwing away our data, we cache it. We keep it in some big, we make our training set an explicitly stored object. We have some experience replay memory. And now all we do is at every time step, we're going to sample a state and a value from our experience. So if we were in state S, we're going to sample from this experience. We're going to say, okay, in that state, the oracle said I should do this. Going to sample that from our experience, and then do one stochastic gradient update towards that target. So this is just like supervised learning again. We've made a data set, and now we're just going to randomly sample from that data set and update in the direction of our random samples. That's standard supervised learning. If you get a data set, you always want to randomize over it and kind of, you don't just want to do the latest things. You randomize to remove correlations. So this is taking our non-IID data, our whole trajectory, and it's randomizing it. It's breaking up into all the little pieces so we're not presenting things in the order they arrive, which are strongly correlated. We're decorrelating things and presenting them in some random order and just applying stochastic gradient descent again and again and again and again until, where do we get to? We get to the least square solution. Okay, if we just keep doing this, this thing will find the least square solution. It will go over and over this data again, doing gradient descent, and if you optimize for gradient descent, for example, using a linear function approximator, you find the global minimum, which is the least square solution. So if you go over your data, you get more out of your data. That's the idea. It's very simple. You remember everything, you just keep going over your data and squeeze more from that data, rather than just throwing it away after one step and moving on. So let's come back to the motivating example we saw in lecture 1, which is this recent work we did with in Atari. So in the Atari work, we're now in a position basically to understand exactly what we did. Actually, I mean, the method's fairly simple, and we can see that now we've basically got all the pieces in place. Okay, and it just uses exactly what we've seen so far. So we're going to use basically experience replay and basically Q learning. So it's off policy, which is a nuance from what we've seen so far. But the idea is really simple, that we just remember all of the transitions that we've seen so far. So remember all of our states, actions, rewards, next states that we see. We remember them in some big replay memory. Every step we take an action according to an epsilon greedy policy with respect to our function approximator. We've got a big function approximator representing Q. We'll see the structure of that neural network in a minute. It's just a big neural network that estimates all the Q values. We use that to pick our actions by acting greedily with respect to our Q values. And then every step, what we do is we sample some mini batches from our data set. So mini batches, not everything, but just a few, like say 16 of these, I think actually 64 we do at a time. We take 64 random samples from our replay memory. So remember, say, a million transitions, sample 64 at random, and follow the gradient with respect to those 64 things. And we optimize the mean squared error between what our Q network is predicting, our action value function, and our targets. And the targets are just something we plug in instead of the oracle. And the oracle, the thing which we plug in is like a Q learning target. So it's just like the SARSA targets, but with a max there. Okay, so we're just looking at the error between what we thought would happen according to our Q learning, according to our Q network. So this is our functional approximator. We plug in the error between that and the reward plus the maximization over the actions that we might do next. So this is just like in Q learning. look at the best thing which I might do at the next step. We want to optimize. We want to say, the value now, we want to update it towards the max over all the things that I might do next. So maximize over all the things I might do at the next step. Use that as a backup so that I now think that the value at this point is as good as the best thing I might have done at the next step. So we make things better and better and better. And then we optimize this using stochastic gradient descent. Now, I said earlier that, that methods like SASA and TD methods can blow up with neural networks. However, this method is stable with neural networks. And that's one of the contributions of why this worked so well and previous methods just didn't and blew up. And so there are two tricks that make this stable compared to, say, using naive Q-learning, which are these highlighted points here. So the first point we've already seen, which is experience replay. Experience replay stabilizes these neural network methods because it decorrelates the trajectories. So instead of seeing these highly correlated parts of the trajectory, one after the other, we randomize the order in which they arrive, and now you kind of break the correlations and you get much more stable updates. And the second idea is to do, basically, have a second network. So we actually keep two different Q networks, and with two different parameter vectors. And we basically freeze the old network. So we remember our old network, we freeze that for a while, and we use the targets. Basically, we bootstrap towards our frozen targets. We don't bootstrap towards the latest, freshest targets. We bootstrap towards our targets from some steps ago. And that also stabilizes the process. It basically makes it just like supervised learning for the course of one iteration. It's like for a while we move towards the Q values with respect to our old network. And then after we've spent, a few thousand steps updating towards that old network, we switch it around and we make our old network equal to our new network and reiterate that procedure. So we never bootstrap directly towards the thing which we're updating at that moment, because that can be unstable. There's a lot of correlation between your targets and your Q values at that moment. And with neural networks, that again can cause things to spiral out of control. Okay. I'm sure there'll be questions right now, so someone ask. Good.
Sorry, I just don't understand the last part where you said it's a new network that we're bringing in the same
Okay.
values, but
Good, okay, I realized I was rushing that, so let me just spend a moment to say it more clearly. So we have two parameter vectors. We have any iteration I. Okay, what this is saying is we're going to optimize the loss function for that iteration. And what we're going to do is we're going to update our latest parameters, wi. What we're going to do is we're going to remember some old parameters. So we're going to use some old parameters from, say, 1,000 steps ago. The old parameters are going to be used to generate our target values. So we're going to bootstrap the oracle now. Is basically going to, the thing that we substitute for the oracle basically makes use of some old parameters. We don't use our freshest, most recent parameters in our target that we're plugging in place of the oracle. We use some fixed old values. And the reason is that we want to fix this because it gives us a more stable update. We don't want the danger is that with TD learning is that every time you update your Q values, you're also updating your target values. Like if this network and this network are the same, every time you update your parameters a little bit, you're changing the targets to which you're moving them. And with nonlinear function approximation, that can actually spiral out of control. And so all we do is we stabilize that process by freezing this guy to be some old value, and we just update a little bit towards the old frozen values.
so what stage do you go back by? What is the parameter that you choose?
So it's a tune parameter where we basically have one fixed schedule for across all games, where every few thousand steps we move on to another iteration and adjust these things.
So you don't update them kind of dynamically, or the frequency is not dynamic?
You can also update them smoothly, but all the experiments I'll talk about were like a switching. They were just kept frozen. You essentially are then doing supervised learning towards these targets. It's like your targets are frozen for a while. This is also called fitted Q iteration, this idea. You freeze your targets, you update towards those targets, and then you switch in your targets to, your old targets become your new targets. You swap your Q network.
So you wait until you update it to the frozen one before you update.
You don't completely wait. You never get all the way there. This is some enormous neural network, but you just wait some period of time, and then you swap, and you find what works best in practice. I wouldn't claim this is the most aesthetically satisfying idea. But in practice, it stabilizes everything. And the experience replay is really important as well. So just to say, this is the architecture that we use. So it's a big convolutional neural network. If you don't know what a convolutional neural network is, it's just something where you take typically an image, and you have some neural network with shared weights that's applied to the entire image, region by region. And at the end of it, we output key values for all of our different actions of what the joystick might do everywhere. And we use the same neural network with the same hyperparameters, same step size, same schedule, same rate at which we update things across 50 different Atari games. And these were the results. So this is from the Nature paper, which came out last week. And you see that basically this is ordered by how well we do compared to a human tester that we had in-house, like an expert human games player. All of this point here, everything to this side of it, we're basically doing better than our expert human in-house game player. Everything to the right, we're doing worse. There are some games which we do horribly at, like Montezuma's Revenge, just turns out to be really hard. A lot of games where we do, way better than human, like in video pinball or things which are very twitchy. So the algorithm is robust. This indicates the robustness. How well do those two ideas help to stabilize it? So we see experience replay makes a huge difference to the stability of the algorithm. This is the performance on, say, 5 different games with and without replay, and with and without this kind of idea of switching the queue networks. And this shows that both of those ideas help, and the combination of the two of them makes it the most stable and effective. Okay, so all of this was just an example of one simple idea, which is stochastic gradient descent with experience replay as a way to squeeze more out of the data that you've seen so far. I just wanted to make that practical. But what, are there methods where we can jump directly to the least square solution? And the answer is yes, for the special case of linear function approximation. So in the remaining few minutes, I just want to give you a flavor of what that looks like. Okay? So it's... So why should we care about this? We have this method of experience replay. It's very effective. It's incremental. It's any time you kind of do as much replay as you want, and you get closer and closer to the solution. But sometimes it can take many iterations to really get to that least square solution. And if we really are using linear function approximation, there's at least with more computation per iteration, like you can do a little bit more in one step and jump all the way to the correct least square solution, closed form. Okay. And so it's like you can do your policy evaluation step in one jump. And so it looks a bit like this. So I'm just going to do it with one case, like using the oracle again, and then you'll kind of see how to plug in all of those different estimators, whether it's so we're going to consider some oracle, again, v pi t. This is at time step t. What's the oracle say the value was? And then you can plug in, again, your Monte Carlo estimate or your TD target or your lambda return. You can plug in anything you want there. But the idea is really simple. The idea is just to say, at the minimum, at the least square solution, what does it mean to be at the least square solution? Well, it means that we're not going to change our weights anymore, like that we wouldn't choose to update our weights in any direction anymore because we've reached the minimum. Like if we were to keep going over our data again and again and again, we wouldn't make any more changes because we're happy we've reached the best solution we can get to. Okay? So another way to say that is that if we take the expectation over our data set, like this sum squared error, of our updates that we would make, we would want the sum squared error of all of our updates over a whole data set to be 0. We don't want there to be any pressure to change this thing. If this was not 0, if this was positive, we would still want to be moving. We'd still choose to change our weights. So that would mean we haven't reached the least square solution yet. And then the rest of this is just expanding that. Okay, so this is unwrapping the sum squared updates. So this is. Sorry, I said the sum squared error. What I meant was the expected update. Expected update. And the update depends on the sum squared. So if we unwrap the expected update and look at the update that we're making over a whole data set, like how are we adjusting the weights over a whole data set, we're basically saying for each sample, we've got, this is our update. We've got, like for each time step, we're moving a little bit in the direction of the step size times the error between our linear function approximator here and the oracle multiplied by the feature vector. That was our update. the linear, you can go back up and check if you don't believe me, but step size times error times the credit, the gradient vector, which is just the features in the linear function approximation case. And we want the sum of all of these things to be 0. We want the average gradient, the average gradient of our objective function to be 0. And so we just collect these terms now. We've got one term here, and another term with this x times this x here. That's just collecting terms. And then we see that only one of these depends on w. And so we've just got this big matrix here, which is the outer product of your features. And so we can invert that to get the solution for w. So with a little bit of linear algebra, you can start off with this idea that you want your update across your whole data set to be 0. With a little bit of linear algebra, you can see that you can bang, just by inverting a matrix, you can get the right solution. Now, inverting a matrix, we've been avoiding doing this because it's expensive. But the cost of this doesn't depend anymore on the number of states. Like depends only on the size of our feature vector. So if we've got a small number of features, this is reasonable. So inverting it takes order n cubed. And better still, you can use something called the Sherman-Morrison-Woodbury trick for incremental matrix inverse. And you can do this in n squared time. So it is possible to get more efficient updates that's got quadratic cost in the number of features you have. So the point is you can go bam, straight to the solution of your least squares. In other words, squeeze the maximum juice out of your data with your linear function approximator, find the best weights. And sometimes this is better than experience replay. Like if you've got a small number of features, but some complicated history of a lot of experience, this might be cheaper to do. If you've got a lot of features, it might actually be better to do experience replay. You might get closer to the solution by doing some amount of experience replay. Maybe I've had a lot of experiments where, just after 5 or 6 repeats over your experience again, you already get close to you extract most of the juice out of the data you've seen. And so you can really get an awful lot with experience replay. But this is also appealing because bam, in one go you get right there. That's specific to linear function approximation. Okay, so as I said, we can plug in Monte Carlo returns, we can plug in TD targets, we can plug in the lambda return, and you end up exactly the same updates. This is just plugging in the same idea of making the update equal to 0 overall, and then solving for that update. And you end up with algorithms called least squares Monte Carlo, least squares temporal difference learning, and LSTD lambda. And so how do these fare in terms of convergence? Well, they actually have better convergence properties than the incremental ones. So in particular, so they can't be applied with nonlinear function approximators, but they do converge both on and off policy to the right answer. So they have less issues compared to TD with this off policy case. They, bam, get you the right answer. Doesn't matter if you're learning off policy. And then finally, I just want to say that how do you actually use this in practice? Well, you apply an algorithm called LSPI, least squares policy iteration. And again, we're back to our familiar approach to doing control. Like if you really want to solve for control, so far we've just talked about how to do policy evaluation. We solve for the least squares fit to our current policy. But what if you want to use that to do control? Well, now we're just going to plug this same idea in again. We're going to replace our policy evaluation step by a least squares approach to learning the action value function. So we want to find a least squares fit to Q. We replace our V with Q, and now we can basically come back to this approach here. We're going to start off with some weights for our linear combination of features, act greedily with respect to our Q, and then do our least squares fit to all of the data we've seen so far, generate a new Q value, act greedily, do a least squares fit to all of the data we've seen so far, and iterate and so forth. If you do this in the right way, it converges to the optimal value function and the optimal policy. So there's a few more details in the slides which roughly just outline a little more detail on this algorithm. It's called least squares policy iteration, and show that this also has, you still have some issues. I mean, when you move to control, this still can chatter, so it's not like this solves all the convergence issues. And then I just want to show one final example, which is like this random walk type example with some more complicated dynamics. So this is a problem with like 50 states, and they're just, so 50 states, and it's like a replica of this diagram with these different dynamics over 50 states. And now we just say there's 2 good states that we want to get to. So there's a reward of +1 if you reach state 10 and state 41, otherwise no reward. And we're going to use function approximation with some kind of radial basis functions, some Gaussian spaced around, kind of generalizing across some of these states. So we're kind of, we don't have a separate value for each of these states, we're going to generalize across them. And now we're going to apply LSPI to this chain walk. And you see in just a small number of iterations, so this is only 7 iterations, it's finding the optimal value function and hence the optimal policy. So here you see this is basically showing the state space along this axis. And so you see here's the good state, state 10, here's the good state, state 41 or whatever it was. And it very quickly picks out the shape of this. So the blue and the red represent the 2 different actions of going left or going right. And and so the other parameter dashed versus solid is whether it's the true value function or the approximate value function. And you see that it very quickly figures out the perfect shape to this thing. And it's approximate, it's not like a sharp peak because the value spreads out a bit, and also because we're using function approximation. It very quickly gets the structure, like, evaluates its starting policy, ends up with a shape like this, acts greedy with respect to it, ends up evaluating that new policy, gets a shape that looks something like this, improves its policy with respect to that, ends up with some a new value function and so forth, and after just a small number of iterations it arrives at the right answer, and hence the right policy. This shows you whether it chooses to go left or right, and you see that by iteration 7 it's already making the right decisions. Even earlier, in fact, it gets the right decisions in this space, where red is right and blue is left in this case. So that's it, all done. Next time we'll talk about policy-based methods for scaling up using function approximation, and see you next time.